Oh wow, it's a hot day outside. I think I'm going to pour myself a glass of water. Nothing like crisp, cool water. I wonder what happens if I take this water and spin it around in a circle. Will it fall out? Let me find out. How do you do that? All right, let's take a look at what happened with the forces in that situation. Here we have a diagram of my cup on the end of the stick going around at a constant speed. I tried to make sure it was a constant speed. We have the water in the cup right here. We know for things moving in a circle or a circular motion, the centripetal acceleration depends on the radius and the speed that it's moving. And by using that, we can come up with the centripetal force acting on an object depends on the mass, the speed that the object is moving, and the radius. Now, we're going to start looking at it for this first section right here. As it moves upward, the water kind of sloshes back against the side. We can add a little bit more water because we want a full glass. The direction of the centripetal force is always going to be towards the center. We're going to do that in red. Centripetal force is going towards the center. What other forces are acting on it, though? We have to include the weight at all times. That's weird. How can we get a force acting on it towards the center, but the weight's acting downward? What's actually happening is the bottom of the cup is forcing the water, is pushing on the water and forcing it to accelerate in this direction. Basically what the cup is doing is it's kind of pushing it around. All this water wants to slide this way, the bottom of the cup is forcing it this way. So that's where we get the centripetal force from. As we move up towards the top, in this point, from here on, the force is decreasing. The centripetal force itself is going to remain the same, but the normal force from the bottom of the cup is going to decrease. We'll see this as a pattern when we get throughout. Again, the centripetal force is going to remain the same. It's just going to switch from one thing to the other. Right now, the normal force from the bottom of the cup is going to decrease. When we get to our top position, the force is going to be entirely due to the weight of the water. The weight acts downward. It's going to really be the only force acting towards the center of our motion here. So we know that the centripetal force is going to be equal to the weight of the water. From that, you can use that if you were ever to try and solve for a problem. What actually is happening to the water itself is now the water is getting pushed, 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 and at this point here, it wants to stay moving at that constant velocity, and what's going to happen is as it moves forward, gravity is going to be acting on it, so it actually kind of is going to follow a curved path. So if you were to go at the minimum speed of this for this cup, it's the minimum speed that basically for this next part, all you're doing is catching the water as it falls down back into the cup. Next, so I said as we're going through here, now the force, the normal force from the bottom of the cup towards the center on the water is going to increase. and it's going to increase the entire way through. So what the water is doing is you're catching the water in the cup as it moves down and around. And then what you're doing is you come back down here to the bottom. Now, you still have the weight of the water acting downwards. You need to have the normal force, or you need to still have your centripetal force acting towards the center. In this case, because the centripetal force acts towards the center, the force of the bottom of the cup on the water, the normal force right there, is going to be twice the weight. Once again, we have our centripetal force going inward. We know from up here that it's equal to the weight. Because the weight now is directed downward, the force of the cup on the water needs to be twice the force of gravity. So if you were thinking about a scale, and if you were standing on a scale, as you go traveling around, up here at the top, you would weigh nothing. You would almost be like kind of just hovering over the scale. You'd be the scale now starts to catch you. You start weighing more and more and more and more and more. And when you get down here at the bottom, you're now going to have twice your normal weight. Because you're moving in a circular motion, there needs to be some force directed inward that's going to cause you to accelerate and change your motion. So let's look at that once more. I have my delicious cup of water, and I'm going to do it at a smaller radius this time. So now I'm going to go around in a circle, like that. Now, in this case, as I swing it around, if I decrease the radius, this distance here, I can also move it at a slower speed. As before, now think about it at the farther length, longer radius, it's going to be covering much more distance in the same amount of time, so it therefore needs to be moving much faster. What happens if I don't move it fast enough? At this point here, the cup will no longer be able to catch the water as it's going to fall too quick, and therefore it will come out of the cup. Oh no, I need an umbrella. Have a great afternoon, and I'll see you guys all in class tomorrow.